All right, so the first question I'm going to cover is, can you go over the haloform reaction if we don't have excess? So let's say I have something like that, right? And actually, we've seen this one before, so let's do it a teeny tiny bit differently. Let's have something like that. And when we're doing the haloform reaction, we have Br2 and a catalyst, right? So if we have NaOH as our catalyst or any other kind of base, you can assume that this is an excess, but 9 out of 10 times he will tell you excess, right? And we know that in this case, we go on to fully brominate like so. And then didn't give myself enough room. And then once we've fully brominated, we have to actually kick off that leaving group, and we get an OH instead, right? If we don't have excess, it's not going to be a haloform reaction. So if I give you the same thing, right, and I give you Br2 in H3O+, that's no longer the haloform reaction. That's just a bromination. And we are only going to brominate one time. So that's the difference. So the follow-up question is, will it always have excess? Yes. So the haloform reaction will always need to be in excess, aka base. It won't be called the haloform reaction if it's not under those conditions. You're very welcome. Okay, so then the next couple of questions were about NMR. So let's actually I'm just going to make a duplicate of this so I don't mess it up before I send it to you guys. But let's go through the chapter 9 stuff. So when we're counting signals, I believe that's what the person asked. So they wanted to go over signals, especially in a ring, and determining whether they are the same or not. So for example, let's say we have this benzene ring to start with, and let's say I have a methyl here and a methyl here. So the two methyl signals, even before that, actually, I'm going to get ahead of myself. So what's the first thing we have to look at for this kind of question? Symmetry. Yes, exactly. So we have symmetry right down the middle here. And so we know that this carbon and this carbon are exactly the same. So all 6 of those hydrogens are going to be under the same signal. So we'll call this signal number 1. And it is a 6H signal because the integration is 6. So then the next ones up are these two, which are the same as one another, but they're not the same as anything else. Oh, wait. I don't know what I'm talking about. There's only one hydrogen, and it's not the same as anything else, so it's all by itself. And then here and here, because of symmetry, they're the same. And this last one, again, is all by itself. And then let's say we have a ring like this, right? So now, do we have symmetry? No, we don't. So things are going to be a little bit different. The first signal we're going to talk about is, let's just start over here. So these three hydrogens are going to be different than everything else, but they are the same as one another. So that'll be signal number 1. And what is the integration of this signal? You guys, wait a second. Okay, yes. So it's going to be 3H because there are 3 hydrogens in that signal. Next up, we're going to look at this signal right here. There's going to be 2 hydrogens. And so this is a what kind of center? It has to do with chirality. Well, it is geminal, yes, because they're both on the same position. But furthermore, they're potential chiral centers, so I like to put a little P. All right, so those 2 hydrogens can either be enantiotopic or diastereotopic. What do we look for to distinguish enantio and diastereotopic? A chiral center somewhere else, exactly. Do we have another chiral center? No. So the relationship between these two is what? Enantio or diastereo? Enantio. Perfect. Alrighty, so next up, there's no hydrogens here, so we move on to the next one. And this one is all by itself, all alone. Same thing here. Same thing here. And then I'm running out of colors, so let's go up to this methyl next. So how many signals, how many hydrogens are there in this signal? 3, so we're going to say that's 3H again. And last but not least, just kidding, we already did red. Last but not least, we have that orange hydrogen. So all together, how many hydrogen signals are there? 7. All right. And so now we're going to go back through and count carbons. So carbon number 1. Not just count carbons, but count carbon signals is what I meant. So that'll be number 2. We have this extra one here. It didn't have a hydrogen, but it still counts as a carbon signal. And then we have 4, 5, 6, 7, 8, 9. So we have 2 more carbon signals than hydrogen signals because this carbon and this carbon don't have any hydrogens present. And then someone asked to do one kind of similar to this, but adding another substituent. So yes, we can do that. Any questions on the 2 that we have done so far before we move on though? I'll start. So yes, I know people were asking for specific questions from different packets. So I want to go over the concepts first before I go into the practice problems or anything like that. So once I move there, remind me what question you wanted to do, basically. And someone asked, is mass spec going to be on the exam? Yes, it is. It's part of chapter 9. There's probably going to be like 2 questions on it. All right, so let's do first non-symmetrical by adding a third methyl or substituent. Yes. So here, here, and then sure, I guess let's do that. Okie dokie. So first thing is first, do we have any kind of symmetry going on here? No, not really. So all of these methyls are now going to be different. So this will be signal number 1, and it will be 3H. This will be signal number 2, and it will be 3H. And this will be signal number 3, and again, it will be 3H. And for the other ones, the reason I'm not writing what the integration is because it's just 1. So there's no point really. Okay, so now going into the ring. So we have this hydrogen all by itself. And then we have this hydrogen all by itself. And I'll do an orange, I guess. This hydrogen all by itself. So altogether, how many hydrogen signals do we have? I almost asked for carbon. Oops. 6, yes, exactly. So then when we go back and count carbons, 1, 2, 3, 4, 5, 6, and let's not forget the 3 carbons that don't have any hydrogens attached. So 7, 8, 9. So we have 9 carbon signals. How do you feel about this one? To the person who asked for it, are you happy? Okay, good, good. All right, so while I draw out the next one, I'm sending you guys the attendance link. You can either do it now or after, whatever you guys want to do. Just don't forget to do it, please. Okay, so we're going to do the cyclobutadiene one, or not diene, cyclobutane. So do you want to do cis or trans or both? Because someone had asked for the 1,2-dimethyl cyclobutane. Either or. Okay, cool. So we can do the cis example, and then I have the trans example already drawn out. So the way I like to do it is kind of 3D so that you can see what's happening and why everything is the way it is. So I draw it kind of crooked like that. And our methyl groups are pointing up. And so now all of the hydrogens that are on either methyl are going to be exactly the same because we have this lovely line of symmetry here. And they see the same environment. So I'm going to go ahead and draw those out. I don't know why I decided to start making all the lines so thick. Ta-da. And so opposite here, pointing downwards, we have 2 hydrogens, right? can we say that the hydrogen pointing down here and the hydrogen pointing down here are the same? One person answered, but I want a couple more people, please. So can we say that this hydrogen and this hydrogen are the same? So yes, because of symmetry, but also because when you think about it, they are seeing the same environment. So this hydrogen sees two hydrogens, this one is seeing two hydrogens, and they are both attached to a carbon that has a methyl. So the concept is symmetry, and then this is how we kind of understand like why that makes sense. So then when we look at these two carbons, each of them has one hydrogen pointing up and one pointing down. So if we think about it in the same type of symmetrical and also environmental type of way, let's call this H, A, B, C, and D. Which two do you guys think are going to be the same? So give me one of the pairs. A and C, okay, and then B and D. I agree. And so we're saying that HA and HC are going to be the same signal. And why is that? Help me put it into words, please. Exactly. So the purple group is pointing up and it faces the two methyls, versus the two pointing down are facing two hydrogens. And someone else said it in a great way as well. They're on the same plane, so they are seeing the same environment. Exactly. And again, the reason this is true is because we have symmetry and because both of the methyls are cis, they're both pointing up. Okay, so then the follow-up question to that is, so would the geminal hydrogens be heterotopic or diastereotopic? So since there's a line of symmetry, we don't have true chirality. So it's kind of hard to give those names like heterotopic, diastereotopic, things like that. I believe we would just call A and B heterotopic to one another, and we would call A and C homotopic. I don't think we can use an enantiotopic and diastereotopic because it is a meso compound. Sort of, kind of, does that make sense? No, he wouldn't ask you a question like that, like, is it heterotopic or diastereotopic? I mean, no, he wouldn't ask you. He would just tell you to like count the signals, so he knows that you know the general idea. And if he asked you like, are HA and HB the same signal, you would just say no. But he wouldn't ask you for like the specific name. Okay, cool. Alrighty, so if we go back. All right. So, sorry, I'm trying to read and like not have it be quiet at the same time. So someone had asked for signal counting, and I know we covered the question about the cyclobutane. So are you guys good with counting signals, or do you want to do like a couple more practice problems before we go on to the next topic? Or I guess the practice problem sheet, because I know people had questions on that. Oh yes, and we can do the trans one. I have it already drawn out, so I don't want to redraw it again. So the cis and the trans are different because of where the methyls are pointing. So we still have a line of symmetry here, but it's rotational symmetry instead of like just flat symmetry. You don't really have to know that. Just people get confused when I say it's still symmetrical. So now the methyls are still the same. These red hydrogens are still the same. The difference comes here. So what you guys had said is for the cis one, the two on top are the same and the two on the bottom are the same. And when it's trans, we do kind of like a flip-flop X shape. And the reason is this blue one pointing up sees a methyl and a hydrogen. The one pointing down only sees two hydrogens. So those are not the same. This one on top also only sees two hydrogens. So this is not the same as this one anymore. It's the same as the one pointing down. And the same is true for the blue hydrogens. So if we were to fill in how many signals there are, on the cis one, how many hydrogen signals do we have? 4, yes, exactly. And how many carbon signals do we have? What do y'all think? For the cis one, how many carbon signals do we have? So now we actually have 3 signals because we have these methyls, which are the same, these carbons, which are the same, and these 2 carbons, which are the same. So we would only have 3 carbon signals. And the same exact thing is actually true here. So we have 3 carbon signals still. And even though the orientation of these hydrogens is different, we end up still getting the same number of signals. So it's still 4 hydrogen and 3 carbon signals. Good? You are very welcome. I'll leave this up for like 1 more minute so you guys can take a screenshot or do whatever. And then we can go on to the practice final. Because I know some people had questions on that, so I genuinely have like way too many files. Okay, so I think someone said go over number 10, and then someone else wanted 2 questions from here, but I forgot what they were, so please send it to me in the chat. All right, so we are looking at this specific molecule, and we are trying to count signals. And I know you guys have already seen the answer, but let's pretend you've never seen it before. So this is ugly, but I tried to do it sort of kind of 3D-ish. The first hydrogens we're going to go over is this one and this one. So if you're anything like me, you kind of struggle to see like how these are related to one another and like things like that. So people are like, yes. Okay, so exactly. So first of all, we know that there is a line of symmetry in the molecule, but it is internal. It's not across the whole thing. And that is down here. So this half and this half are exactly the same. And the only thing that we have to consider is, all right, this one pointing forward sees this stuff. This one pointing backwards sees this stuff. So these should be 2 different signals, right? Wrong. And I kind of struggled with understanding that, but basically the difference here is that we have free rotation here. So basically this is spinning all the time, which means that all of these hydrogens are going to see the entire environment basically at all times. So we're going to say that all of those 4 are equal. This is going to be signal number 1. And what is the integration? AKA, how many hydrogens are in this signal? 4, exactly. Sweet. So then if we go up here, there's no hydrogen signals, but there is a carbon signal. So let me do that while we're here. We have 1 carbon signal, but no hydrogens. And let's go to this side first. We have 2 H's. So this is a potential chiral center. And we need to know, are there any chiral centers in this molecule? Yay or nay? No, there are not. So what's the relationship between those 2 green hydrogens? Enantiotopic. Sweet. All right. And then we know that these 3 hydrogens are just chilling. They're doing their own thing. They're entirely their own signal. And so now, oopsie, we have this carbon right here, and it has 1 hydrogen. That's going to be all by itself. Now we have a double bond, and this is where people usually get tripped up. So we're going to spend a little bit of time on it. So we're going to call it HA and HB. HA and B are on the same carbon of the double bond. And that double bond has 2 unique groups on the other side. So what is the relationship between A and B? Yes, they are diastereotopic. Awesome. So why do I use up so many colors? We have HA and HB, and their relationship is going to be diastereo. So they are 2 completely unique signals, but this carbon right here is just 1 signal by itself. So let's count together. How many hydrogen signals are there? 1, 2, 3, 4, 5, 6. Do you guys agree? Yes? Okay, cool. So what about carbon signals? And yes, I can go over the diastereomer thing one more time. But yes, we have 6 carbon signals. All right, so the reason these are diastereotopic is because they are present on the same carbon of a double bond. So whenever we have a double bond, we're going to cut it in half this way. And the 2 hydrogens on the same carbon can potentially be diastereotopic. This one on the other side will never be diastereotopic to one of these. It's just random. We don't like it. All right, so now that we have 2 hydrogens here, the next step is to look at the opposite carbon, and the other carbon has to have 2 different groups. It doesn't matter what those 2 groups are, as long as they are not the same as one another, aka they're not symmetrical. So if it has 2 groups that are not symmetrical and 2 hydrogens, we can go ahead and call that diastereotopic, which means that they are 2 different signals. I know I said it kind of fast, so I can repeat it again if you would like. But does that kind of help? For homotopic, So yes, if we had something that looked like this, so they have two of the same groups and two hydrogens, these would be homotopic. And if we had something like this, where there are two different groups and two hydrogens, but those two hydrogens are on two separate carbons, then that would be heterotopic. Make sense, kind of? Cool. You are very welcome. And then I just realized the other person who wanted to do practice problems was in the chapter 11 and 12 handout. So does anyone have any questions, like any specific questions about the practice final before we go into that handout? I'll give it a second because I know typing is rough sometimes. All right, we can always go back to this if you guys want. Don't be shy. Don't be too afraid to ask. But let me find chapter 11 and 12. There we go. All right, so please remind me. I didn't even have to say it. You guys already have it. Okay, so someone, or two people asked for specific problems, and we can just go back. Don't apologize. That's completely okay. I know it takes a while to like type things in the chat. So we're just going to do these two, and then we'll go back into the practice final. Okay? All right. So we're going to do 13 and 40. So ooh, good one. All right. So I personally strongly dislike condensed formula, so I'm going to redraw these out. So is this what we're working with? There's a trick here. What's the trick about what I drew versus the reagent that they gave us? So I'll say that one more time. So what's the difference between what's given here and what I drew? I specifically did a trick that a lot of students mess up. What functional group is this? Carboxylic acid. What did they give you here? Yes, we're missing an extra oxygen, and that changes the question entirely, and a lot of people make that mistake. So here, what they're giving you is not a carboxylic acid, they're giving you a peroxy acid. So we know, someone already said this in the chat, but a double bond plus a peroxy acid equals an epoxide. So let's call this A and B. So right here, we made A. So now we're reacting our peroxide, or excuse me, our epoxide with CH3OH and HA. What does HA stand for? Acid. Okay, guys, let's remember back. What is the preferred order of attack in an acid catalyst. 3, 1, 2, exactly. So in this case, this side is tertiary, this side is primary. So which side are we going to attack? Tertiary, exactly. So I'm going to rewrite this here just because I didn't give myself enough space. And I want to like work it out with you guys. So here we have tertiary, here we have primary, and we're going to attack the primary side. So before we actually do any attacking, we're going to do something called the activation step. And we are going to take that hydrogen and we give that a plus sign. And the reason we do that is because we make it a better leaving group, aka it's easier to attack and break the ring. So now we are left with O-, which will come in and attack the tertiary side. So if we attack the tertiary side, we are going to break this bond right here. And we're going to kick that open. And I always like to number my carbons. So 1, 2, 3. So let me draw a 3 carbon chain. We know on carbon 2 we had another methyl. What are we going to have on carbon 3? One, two, three. So what do we have attached to carbon 3? An OH, precisely. So what is attached to carbon 2? What'll be attached right here on carbon 2? Exactly, the alkoxide, aka OCH3, aka our nucleophile. Perfect. All right. So now we are just looking for the answer choice that fits this. And which of these answers would fit what we just drew? Well, this one has 2 OCH3s. That's gross. Ew. This one has an OH and an OCH3. OH, OCH3. This one only has 1 oxygen. This one only has 1 oxygen. So we know those are wrong. So we're stuck between C and D. And the one with correct orientation is, in fact, C. You are correct. Ta-da! So I'll leave this open for a second. To the person who requested this one, any questions, comments? Does this make a little bit more sense now? So as far as the numbering goes, I just did it like that because okay, so the way I number it here to keep track of the final product is not like IUPAC numbering. It's just an arbitrary way of numbering that makes me keep track of my carbons. So you could have also numbered it the other way around. Okay, cool. So the next one is number 40. So let's go down. So I'm going to just delete that. Delete that. So hold on. Let's go back up here. So someone asked, wouldn't there be 4 carbons? Yes. Oh, you are so right. You are so right. I somehow numbered it and still drew the wrong number of carbons. So thank you for pointing that out. No, don't be sorry. Thank you for pointing that out. I just made a mistake. So in case I confused anyone, yes, there was only supposed to be 3 carbons there. I made a mistake. Good catch. Alrighty, so back to 40. I feel like we're scrolling forever. Okay, here we go. So here we, I don't know if you guys heard the sound my laptop just made, but that kind of scared me. So we have SO2Cl. So what kind of group is this? Hint, it's a protecting group. What's the name of this type of group? Mesylate, exactly. And we knew this is mesylate, not tosylate, because methyl. That's how I like to think about it. And so in this first step, when we use mesylate, do we keep stereochemistry or do we flip stereochemistry? Going to keep it. All right. And so this next step, if we have just a nucleophile, what type of mechanism are we going to do? And this is one like from Orgo 1. You guys remember? SN2? Right? So in an SN2, it's one step. So do we keep the stereochemistry or do we flip it? Flip, exactly. All right. So if we keep it the same and then we flip it, overall we have a flip in stereochemistry, and we have it drawn in a really weird way here. So it's not like a regular wedge and dash. So in this version, all we're going to do in order to flip the stereochemistry is flip the 2 wedges. So we flip the OH from the right side to the left side. And so which answer shows that? Oh, my bad. I'm just being silly today. I think I'm tired. So we don't just add an OH. We replace that OH with whatever our nucleophile was. So in this case, it was this. So now, which of these answers represents what we just drew? A, exactly. I would agree. Sorry for the little flip up at the end. But does this make sense? Was this helpful for the person who had requested it? Anything you want me to go over? Okay, cool. Yay. All right. So there were. All right. So someone asked for tosylate, it would flip, right? So no, mesylate and tosylate are going to be exactly the same. So mesylate Keep. And PBR3 is going to flip. And this is only for the first step. You're very welcome. Okay. So, where is... Okay, so going back to the practice final, you guys wanted to do 26 and 23, and then you guys want to do on chapter 17, 18, packet, you want to do number 68. All right, so we have like 3 minutes. So we're probably going to have time for one of these, and then we can finish going over this in the next session, which you guys should have access to as well. But before we do that, someone said, wait, I thought tosylate and mesylate swap configuration. So let's actually go back to that real quick so nobody's confused there, because I know that's a weird one. Okay, so for protecting groups, in the first step, mesylate and tosylate are going to keep the stereochemistry. In the second step, which is an SN2, that's so weird. In the second step, we're going to flip. So overall, we have a flip in configuration, but here we're going to keep, here we're going to flip and flip, so then we end up keeping the same configuration. Cool. I know it's really easy to flip-flop that in your brain, so any questions on this? Are we good? Alrighty, cool. So it's technically 1:50 now, and I don't want to start the next question and make the other people, like the next section, late. So, if all you guys want to go on to the next session, and I will cover all the questions I wrote down, that would be cool. So I will see you all in a little bit.